average power absorbed by each resistor. Okay, so there are two sources in here. And when you're doing a problem like this, one of the first things you probably think about is, if you just want power dissipated, only the resistors can dissipate average power. Is everybody clear on that? Now, if you're doing this, the obvious thing is we want the current, and I don't care how you do this, we would like to have the current here, I'll call that I1, and the current here, I2. It doesn't matter how you label these, but that would be the ideal. If we had those currents, we could find the amount of power dissipated by the 2 ohm and dissipated by the 4 ohm. First, do we all agree on that? All right, now how do you want to go about getting those is the next question. I think everybody can see that you could do this two obvious ways. We could do it with mesh analysis, or we could do it with nodal. Do you all agree with that? There could be two obvious ways of doing this. Probably, I'm guessing now, probably nodal would be the preferred way. I don't know for sure, but I think most of you would agree with that. So if I go down here and ground that, we're 0 volts. Now I'm going to do nodal. If somebody has a strong preference for something else besides nodal, we'll do it, but I'm using nodal. And I'm going to do one other thing too. I'm going to redirect this current this way you'll see why. I'll call that I1, and I'll call that I2, and this will be my unknown potential. I'll just call that V. Do you all agree with that? For nodal now? I'm going to see this right here. I'm going to try this one. This has two sources. In fairness, I'm not going to give you two sources on the quiz. I'm just saying it, all right? The reason is sometimes the matrix equations that result are, there are 2x2 matrix that have complex coefficients in them. And I won't do that to you on a test or on a quiz. But nevertheless, this is a good problem to try to show you how to think about something like this. Now, if we're doing this and we're using nodal analysis, the whole idea is the sum of the currents into a node, leave a node. Do you all agree? By the way, you asked me about this. Did you use nodal for this? I don't know how they did it.
I tried using mesh, I got stuck.
You can use mesh. We could do it with mesh too, but the reason I'm saying nodal, for the most part, with very few exceptions, nodal analysis has the minimum number of steps. Usually, if you need all the currents and all the voltages. Mesh, sometimes you get a little more, you're going to have more steps, and you can have a larger matrix. Now, the easiest possible, if we want just the power associated with one element, would be Thevenin. I'm leveling with you. That's the way to always go. But in this case, we're doing this. What I'm going to do is say all the currents into this node, this would be the only node. Do you all agree with that, class? Equal all the currents out. If I look here, I have 430 degrees going in, and what's coming out? Well, I1 and I2. I'm trying to be clear about this. I don't want to hurry up. I think we can all see the logic on this, right? Now, here's where you're going to have to use some complex, you're going to have to use your calculators to calculate this, and then they're going to be complex numbers. When I look at this, what is I1? Now, be careful. I1 is always going to be the voltage on the point we want the current entering the impedance minus the voltage on the point it's leaving the impedance over what? The difference in the two voltages. You all agree with that? I mean, over the impedance part. So here, I'm going to have 430 degrees is equal to I1, and that's going to be V minus 12. You'll notice I grounded that, so every voltage is with respect to 0 being the ground. You all see that, class? That's going to be V minus 12. You don't need to put the 0 degrees. Over 2 minus J1. And then for I2, it's just going to be what? V over simply 4 plus J1. You all agree with that, class? Now here's the thing. From here on out, it's up to you how you want to do it. When I look at this, I'll go ahead and just expand it. I'll show you what I'm thinking. So I have 4 at an angle of 30 degrees. is equal to, and now what I'm gonna do is take V here and break it out, and now I have 1 over 2 minus J1, and I have plus 1 over 4 plus J1. And then I have minus 12 over 2 minus J1. Can everybody follow what I've done? And can you guys in the far back see this, by the way? Can you read this? Far back. Okay. So the only thing I've done is I've broken out V by itself times this coefficient, and then I've broken out this other part. Now this is a value, this is not a function of V, I'm going to take it to the other side. Everybody follow me on this? When I do that, what do I get? So I'm going to have 4 at an angle of 30 degrees. That's going to be plus 12 over 2 minus J1. And that's equal to my V, right, times 1 over 2 minus J1 plus 1 over 4 plus J1. And now, I'm just showing you what I need. I need to solve for V. Do you all agree with that, class? And to solve for V, I have all this on that side. Now I divide by that to get V. Now some of you if you haven't been using your calculators to do complex calculations, now is a good time to get them out and try this. Because you're going to find out there's shortcuts. There's all these tricks. All the way to do this efficiently. And if you don't use your calculators to do this, you won't see some of the tricks. And I'm going to level with you. I don't have a TI. But I think most of this class has TI calculators, either 84 or 83 or 89, or what's the other one, Inspire, or God knows what. But they all do this. It's just, I'm not familiar with it. So if I come over here, and I'll do it right here, I get V, try this on a calculator. So I'm going to get V equal to, and I have 4 at an angle of 30 degrees plus 12 over 2 minus J1. You probably can enter this directly as I'm doing this. You have to divide the whole thing by 1 over 2 minus J1 plus 1 over 4 plus J1. And that should do it. And you should get V as a complex number. Now, I'm going to tell you this much. A lot of times, when you're looking at something like this, these numbers bother you. You know, they do. So one thing, and it depends, your calculators, I think, can just allow you to enter complex numbers. I don't think it's very difficult to do that. Maybe a little tedious until you get used to it. But if you wanted to, I wanted to say this, if you have something like this, 1 over A plus JB, and you don't like that 1 over business, then you just want a real and imaginary part, you can multiply the top and bottom of this by A minus JB and A minus JB. Now when you do that, on top you have A minus JB, but on the bottom you're going to get A squared here, and then you're going to get A plus JAB minus JAB, that cancels. Then you get J times minus J, well that's really minus 1 times minus 1. So it's going to be A squared plus B squared. Now that will break down to a real and imaginary part, because you just have A squared plus B squared in the bottom. So it's A over A squared plus B squared, and then you're going to have minus J over A squared plus B squared, if you want to do it that way. That's called the complex conjugate. How many have heard of this before? That's one method. I mean, people do it all different ways. Irregardless of how you do it, you're going to have to be able to do this and do it efficiently. So I want to make sure you get your calculators out, and if you do this, what do you get for V? Magnitude and angle. 14.38 and an angle of, say that again?
15.52.
15.52 degrees. Anybody second? Second, okay? How many have tried this just now on your calculators? Did anybody have any difficulty? You did? What kind of calculator?
Yeah,
Anybody have an 84 nearby that can help them? Because I don't. Anybody else? I'm trying to get you some help if you don't know how to use your calculator. It's usually not hard. I mean, honestly, it's just being familiar. Your calculators are meant to do this. They're engineering calculators. Complex numbers are part of the deal. All right, everybody with me on this one? Now, if we have that V, I'm gonna ask this, and light at a time. The next thing I'm gonna ask, now hear me, if we have that V, do we have this current I2? How many see that? It would just be that V over 4 plus J1, right? Do we have this current, I1? Yeah, it's just gonna be that V, whatever it is, minus 12, right? And then we divide it by 2 minus J1. How many see that? Trying to be clear about this. We have the currents. Now, if we have the currents, and I'm assuming we can get them. I don't want to spend a whole lot of time on this, but if you want me to, I'll put up the answers, we'll do it all, but I think your answers are provided, aren't they? In this problem, you asked me about this, I think they are. Now, if we have that, do we have the power here? Yes, 1/2 the current squared times 2. Do you agree with that? Do we have the power here? Yes, the average power. 1/2 times the current squared times 4. We have those powers. Now, if we have those powers, then I got a question for you. Do we have this? We have this voltage, right? I want to make sure you see one thing. I want to make absolutely sure you see this. It's very important. I'm going to have to use this board for that. I'm just making the point. We have the powers through the resistors, or dissipated by the resistors, if we have the current. That's the single point I wanted to make. But I want to talk about this source for a second, because this is an area of some concern to me. It should be. So I'm going to go and erase this. So if you have a source as such, and I'm going to show you how, and I could put just the general element, maybe I will in a second, but if you have a source, it doesn't matter if it's voltage or current, okay? I'm going to go ahead and say this source has a certain voltage, V across it, that'll be a peak value, and we're talking about an AC voltage, something that's time varying. And there's a current here. Now, this, I'm going to assume a little bit more about. I'm going to say it's V at some angle, theta V. So it has an angle associated with it. You always plus. It's a time-varying phenomenon. Magnitude and angle, that voltage right there is the peak voltage. This value of I, I'll call it I, but it'll have some angle, theta I. And now I want the power that is associated with this element. Now, if the current was going in the other direction, the power would be positive. You all follow me on this? Maybe I should contrast that over here so I don't confuse any of you and you understand this. Matter of fact, what I'll do is I'll do it right here so you can see it in terms of an element. And this, what I'm about to show you is true generally. But if you have something, it really doesn't matter what it is. And this something has a current going into it, I, at an angle theta I, and it has a voltage across it. You'll notice the voltage that I'm listing is developed with a plus where the current enters and the minus where the current leaves. This is the key to getting the right answer. And this voltage is some value V at some angle theta V. Both I and V are the peak value. Then the power associated with this element, and the average power, I might add, is going to be 1/2 V times I. Those are strict magnitudes. Y'all with me? Then it's times the cosine of theta V minus theta I. Now, if this is something that is an impedance, if it's something that is dissipating power, then that power will be positive. However, if it is supplying power, this will be negative. Do y'all follow me? As a matter of fact, what always happens, if you sum the powers associated with all the elements in the circuit, including the sources, you get 0. The net power supplied, which will be negative, is equal to the net power dissipated, which will be positive. You all follow me? Now this is the way the symbols work. Over here, I'm showing you current leaving. Maybe what I should do is, well, let me go back to the problem. I'm just going to use this. You might as well just use this one. You can't mess it up with using this. You can't. Let's think about that current source. I had a current source here, right? And the current, I believe it was 4 at 30 degrees. Do y'all remember that? We had it a second ago. So this current had a value of 4 at an angle of 30 degrees. And then we got the voltage across this. And the voltage was V. Do y'all remember that? We just calculated that. I'm trying to just isolate on this to show you the amount of power associated with this element. Are you all with me on this class? So, what was that voltage again? 14, was it? I forgot. You gave it to me, sir. What was it? Somebody gave it to me.
14.38.
All right, 14.38 at what angle?
15.52.
All right. Now I'm assuming that's the voltage plus to ground or minus, right? Who's talking to me here? I heard your voice. Oh, there you go. You all with me, class? All right, what's the power associated with this? Well, the current's leaving, isn't it? Now, if we wanted to get the current going into it, follow me? Then what would you do? Couldn't I say that this is actually going to be a current of 4 at 130, and it could be either plus or minus 180 degrees. 4 at 30 plus or minus 180. That's the same thing as putting a negative sign in front of there. How many see that? Are you all with me on that? It is identical. So it doesn't matter, and what I'm going to do is leave it as plus for now. So now I'm saying, I got the current going that way, now I can use that equation to find the power. Now please watch this. So the power associated with that, and if it's negative, it's supplying it. That average power would be equal to 1/2 times V, which is going to be 14, I need your help for this one, 3/8, and then times I, which is 4, and then times the cosine of theta V, well, that's 15.2, or 15.52, pardon me. So this is going to be 15.32 minus the quantity, 30 plus 180, or really I can say 210, right? Minus 210 degrees. So what is this average power? Can somebody give that to me? That's going to be 1/2 times 4, really 2 times 14.38 times the cosine of, and I'll need your help for this, 15.32 minus 210 degrees. What do you get for that, anyone? I think he probably did it this way, but I'm not sure.
Negative 27.85.
Say that again, minus 27 point what?
85.
Is that what he has in the solutions for the power associated with that current? Yes. You all see what I did, class? You can always do it that way. If you need the power, yes, sir.
Can I ask why you're using 210 degrees and not 30 degrees?
Well, what do you have to do here? We had to take what? We had to take, remember it was coming out, right? It was going up, it was 4 at an angle 30 degrees, right? The way I did it is current going in over there, right? So I had to add 180 degrees or subtract 180 from that angle to really account for that change in direction. Do you follow me, sir?
That makes sense.
Everybody with me on this? Yes, sir.
Can you just do -4 without changing the angle?
Yeah. The reason I didn't do that, I'm trying to be real straight about it. I said going in, right? So, you're right about that. Maybe I'm trying to oversimplify it. Yeah, you can do it that way, but the problem is you're not going to get a magnitude in front. Then you got that sign to work. He's right. I'm just trying to make it simple. All right, class, are we clear on that? Oh, you are back. All right, I want to do one other thing today. I'm a little behind here, but for that problem, honestly, I mean, there's obviously many steps to it. The key is getting the voltage, the way I did it. From the voltage, you get the currents. From the currents, you get the power dissipated by the resistors. Can everybody see you can get the actual power associated with the voltage source too, just by getting the current? You all follow me, class? And then you can do that. That's how he did the problem. There's many steps to that. What I want to show you is one thing called RMS values of voltage, or anything. It's called the root mean square. Now, probably in your other engineering courses, they have something equated to this. And the real reason we're doing this is because the RMS values of voltage become something that's very useful to get an idea of the power or the real value of the signal in terms of supplying power, because you can have an enormous amount of peak voltage, but it only lasts for an instant. So what's called the root mean square value, or VRMS, can be very small. It's the same with the current. I just want to define this for you. First, when we take a look at any kind of a signal, I'm going to do one like this. Suppose this is a voltage waveform. It's called a square wave. And the voltage waveform has some value V naught, and it's on for a value tau, and there's a period T. I'm just trying to give you an idea of something that's either at a peak value or it's zero. It's a voltage. And this is going to be some V of T. Well, there should be a way of attaching a figure of merit to give me an idea of really how that could equate to like a DC voltage, something, a battery, in terms of its usefulness for power. And that's my best way of simply explaining this concept. So this is called the RMS voltage, or current. And VRMS for any waveform is equal to the square root, that's where the root comes from, of 1 over the period of the waveform. Now, it has to be a periodic signal. It can't be chaotic, something without any kind of periodicity. So it has to have something, it has to have a time over which it repeats itself, like a sine wave, cosine. Then you would have the integral, and really, technically they go from 0 to t, but it can go from any point to any point plus a period. It has to go over one period. You all with me, class? That has to be the extent of integration. Here, it's going to be the actual value of the voltage, but it will be squared, dt. Then you integrate that over the period. So that's called the root mean square value of the voltage, and it can be a root mean square value of a current as well. How many have heard of a concept like this in your other engineerings? Are you mechanical?
Aerospace.
Aerospace, what is this related to power or something? I'm trying to figure out, say again?
It was to find the turbulence in a
Turbulence?
in a flow.
All right, now this is really an effective value of voltage that tells me, because I'm familiar with a battery, a voltage. Tells me what that could be equated to in terms of a battery's voltage. That's a simple way of thinking about it. You're not going to see that in a book, but that's ultimately what it is. Maybe we'll see. So the next thing is, well, how about an example? So now I'll do a simple example. I'll do probably the easiest one I can think of. I was going to do that one. I'm going to make it even easier in light of the time. Suppose this is the waveform. I'm going to have this is going to be a V of t. It's going to have a value of 1 volt that goes for 1 second. Then it's dead to 2 seconds, comes up, goes back to 1 volt, and repeats itself. You all see this, class? And the thing's been going on forever, so it's just up, down, up, down. All right, the very first thing you have to do is say, what is the period? How long does it take for the waveform to repeat itself? By inspection, class. Can you all read it? Yes, 2 seconds. You're right? Everybody agree with that? Takes 2 full seconds. This should be seconds, but yes. So t is 2, right? Now just execute this. You'll see it. Remember, the peak value is 1, right? Now let's see what happens. So I have VRMS equals the square root of 1 over 2 in integral. Now technically it goes from 0 to 2, but you'll notice the value of the signal is non-zero only from 0 to 1. Do you all see this? So we're integrating only from 0 to 1. Of the value 1 squared, which is 1, dt, right? And you can see that's what? The square root of 1/2 times 1, or it's 1 over the square root of 2, or 0.707 basically. Y'all agree with that? That's how you apply that, the concept and get the actual RMS value of a voltage. Now, the most common RMS value that you'll be wanting to get is the value associated with the peak value of a sinusoidal or cosinusoidal wave. This is the last point. I want you to write it down. The grader back there is very familiar with this, and he can help anybody. Did you have a question? Oh. Okay. So if we have this is going to be, the waveform is just going to be Vm cosine of omega t. So that looks like this. We'd have a peak value of Vm, and it would do this. Can you all follow me on this, class? I'm just trying to show you a cosine waveform. Now, if you look at this, the period would be what? When omega times the period is 2 pi, or the period is simply 2 pi over omega. I'm not going to go on about that. It's just the time over which it repeats itself. Do you agree with this? Now, if I use this formula to calculate, I'm going to cut right to the chase here, the RMS value of that. You would find VRMS at the end of the day would be the square root of 1 over the period. And here's the beautiful thing. When I square a cosine waveform, what do you get? What is cosine of just theta squared? Isn't that 1/2 plus 1/2 cosine of 2 theta? How many remember that crazy trick, right? I mean, we have all sorts of things. It's an identity is what I'm getting at. When you do that, you find you get a constant plus something that varies at twice the frequency. But anytime you integrate a cosine waveform over a period, any number of periods you get 0. Same with a sine waveform. How many know that? All right? If you didn't catch everything I was saying, here's the bottom line. When you do this, and you take the integral here from 0 to t of Vm squared of the cosine squared of omega t dt over the period. After all is said and done, you get this. VRMS is equal to V maximum, or the peak value, divided by the square root of 2. Now, we're going to use this all the time. So, to go from the peak value to the RMS value of a sine or cosine waveform, like that wall outlet, it's just dividing the value of the peak by the square root of 2. And when you look at the actual wall voltage there, what is it about? Do you remember? Anybody? It's called an RMS value, right? How many know it's about 117 to 120, depending on the book you use, right? Well, that is not the peak value. That is the RMS value. You'd have to multiply that by the square root of 2. Comes about 170 volts for the peak. That's the actual peak value. Just so you know that. And I'm going to take it from there next time. But now it's time to get your quiz. Come on down. So everything off your desk. Close book, close notes. Try to spread out. Don't sweat on your neighbor.